Hello, everybody. Sorry about the delay. Just had some extra technical setup today. So today, Graham Manuell is going to be continuing his lecture on point-free topology and constructive mathematics. And it'll be part 3 we'll be listening to today. Okay, thank you very much. Over to you, Graham.
Okay, cool. Okay, great. I don't know if we want to close the door. Okay. Yeah, cool. Okay, good. So since it's been a few weeks, I thought we would start just by recalling some things we covered before. So firstly, we're doing things constructively. So constructive mathematics, it's like classical mathematics, but we don't use excluded middle or choice principles. And we do this so that our results can hold in any topos. So essentially, there are multiple ways to apply our results that give a number of different results whenever we prove a single thing. We spoke a bit about how there's this frame of truth values, which you can think of as the power set of the one element set, but you can't prove this isomorphic to this 2-element set. But maps from an arbitrary set into omega, so I just mean arbitrary functions from a set into omega, correspond to subsets of that set. And while we don't have excluded middle in general, there are certain propositions that you can show are decidable. And this means that excluded middle does hold for those propositions. So certain propositions you can show that either them or the negation holds, but in general, we can't do this. So for the more topology part of the course, so a frame, it's an algebraic structure. It has operations that give finite meets, or operations that give arbitrary joins. The elements of the frame we can think of as propositions in geometric logic, which is this logic of verifiability, in a similar way to how the elements of Boolean algebra represent propositions in classical logic. Every topological space gives rise to a frame of open sets, but the continuous maps induce frame homomorphisms in the reverse direction. So we consider this category of locales, which is just the opposite of the category of frames, and then the maps go in the kind of same direction as the topological spaces. And then just notation, so if we have a map of locales, we kind of pretend that there's spaces in a sense. So we write OY for the frame corresponding to Y, and then we use this F upper star to denote kind of what we think of as being like the preimage, right? Take the preimage of an open set. Okay, and this gives us the corresponding frame map. Good. And then last time, we spoke about frame presentation. So frames are algebraic structures. So like any algebraic structure, you can present them with generators and relations. And this is a very useful way to define locales. It's something that we don't have available in spaces, which is you just kind of come up with some description of the points you want in your space. You define it using geometric logic. And then there's a very mechanical way to turn this into a frame presentation. And then this gives us the frame or the locale that we care about. So here, if we want the locale of real numbers, I've given a presentation. I mean, it's got a few parts, but it's very nice if we can do this at all. And we went through how to do this last time. Okay. So I've told you that you can present frames with generators and relations, but I guess I should really prove to you that this is the case, because if frames were like finite tree algebraic theories, I think you'd probably all be very happy. They're kind of standard ways to do this. But frames are these infinite tree structures where you have a proper class of operations. So it would be good to talk about, for example, why do free frames exist? Okay, so as I say, we want to show that free frames exist. So in other words, the left adjoint is a forgetful functor from frames to sets. And a useful thing to do is to factor this forgetful functor through the category of meet semilattices. So rather than going directly from frames to sets, we go from frames to meet semi-lattices, and then from meet semi-lattices to sets. So we forget about the joins, essentially, first. And then we can take free structures in 2 steps. So first we take the free meet semi-lattice, and then we take the free frame on a meet semi-lattice. So if you have a meet semi-lattice, now this is a finite tree algebra. So, and in this case, it's also a certain kind of monoid. So we can take the free monoid, and then we can quotient to get the free meet semi-lattice. So that's one way we could do it. But actually, there's maybe a slightly more direct way, which will be helpful for kind of thinking about these things, which is that classically, the free meet semi-lattice, or the free semi-lattice, let's not worry about meets or joins yet. The free semi-lattice is given by the finite power set. So the set of finite subsets of the set you start with, and the operation is union. So we want to do something similar here in our constructive setting, but finiteness is a little bit complicated constructively. But this is a good excuse to talk about it, I suppose. Okay, so what do we mean when we say finite subsets? Okay, so finiteness related maybe to natural numbers in some way. Think of them as being like cardinalities of finite things. And natural numbers we saw behave quite a lot like they did classically. And the reason they behave in a similar way is because they have decidable equality. So you can always, if you have 2 natural numbers, it's either the case that they're equal or they're not equal. So this is kind of a version of excluded middle, which we always have. So this is how we're going to define kind of the appropriate version of finiteness that we're talking about here. And this is called Kuratowski finiteness. Now, in constructive mathematics, there are actually a few different notions of finiteness. So we say a set is Kuratowski finite if there's some natural number, n, such that we can consider this, okay, we consider this set of the natural numbers less than n. This we would imagine to be some kind of very canonical finite set. And then there's this ejection from this set onto X. So sometimes these are called finitely indexed. The idea is you can write down a list of all of the elements in the set, some kind of finite list in the obvious sense of the things in the set. Yeah.
Is it not equivalent to asking if there's a bijection?
No.
No.
No. And the reason it's not equivalent is that you can't necessarily tell whether you've repeated something on the list or not. So you might end up writing things on the list multiple times, and it might not be kind of like clear whether or not you've actually repeated something or not. That's kind of the idea. But we'll kind of talk a little bit about this going forwards. But the first thing I want to point out is that if a set's Kuratowski finite, you can tell whether it's either empty or it has a certain element in it, because the set n, if n is not 0, like natural numbers have decidable equality. So n is either 0 or it's not 0. If n is 0, then the set will be empty. If n is non-zero, then the set will not be empty. Now, in general, if you have an arbitrary set, this might not be the case. It might not be true that it's either empty or it has an element. But for Kuratowski finite sets, things work much better. And if it has an element like this, we say it's inhabited. So this is in general a stronger condition than just being not empty, so not equal to the empty set. It's much more useful to be able to say, oh, there is an element, because then you can take that element and prove things about it, rather than just saying, oh, I know that this isn't empty. So one big surprise is that subsets of finite sets don't have to be finite. So this is, I think, quite upsetting sometimes to people when they learn constructive mathematics. But I'll give you an example. So the singleton is certainly finite. But now suppose we have like an arbitrary proposition P, and we consider the subset of the singleton such that P holds. Now, if this were Kuratowski finite, then it would either be inhabited or it would be empty. But this would give us, if it's inhabited, this would mean P is true, and if it were empty, it would mean P is false. So this would be P or not P, which is excluded middle. So if we don't want to assume excluded middle, we can't say that subsets of finite sets are finite. Now, I think one way to maybe think about this that is maybe kind of a way which makes it seem less completely crazy, is that if you think of finiteness as being like the version of sets of compactness. So we've been talking about how to do constructive topology, and so something that will come up soon, probably not this lecture, but next lecture is compactness. And if you have a compact set, this is something, or a compact space, this is something like being finite in some sense, but no one expects that a subspace of a compact space is compact. So why would we expect that an arbitrary subset of a finite set is finite, right? I mean, I don't know.
Another way of thinking about it, right, is just that it's kind of like not completely defined, right? So we say something's finite if we know exactly what it is and it's finite. But in some of these things, there's like some level of uncertainty about what the elements are. And in those cases, they aren't quite finite.
Yeah, I think that's a good way to think about it. Like in this case, it's like we aren't sure whether the element's actually in our set or not. And in our definition of finite, we want to be sure. So it's, yeah, so that's why we aren't calling them finite. I mean, people still sometimes consider them. These are sometimes called like subfinite or subfinitely indexed. But I mean, they aren't really what we generally want to consider. So that's something you need to bear in mind. One thing that maybe might be interesting to point out is that if you take decidable subsets, so remember, a subset's decidable if it's essentially something lying and it satisfies exclude middle. So something either lies in or not. Decidable subsets will generally be finite. So it's really just these arbitrary subsets that cause the problem. Okay, but it does have some nice properties. So it's closed under images. I mean, that should be quite clear. It's also closed under kind of unions of two sets, which is also not hard to see, but actually it's closed under images of Kuratowski finite sets and the unions of Kuratowski finite sets. So it satisfies some nice closure properties. I think we aren't talking about it yet. I think I'll speak about it maybe later in the talk if there's time. But if you have decidable equality, that's the case where you can tell that there are repeats on this list, and then you might get a bijection. So it's really just the fact that you can't necessarily tell whether two elements are equal. That means that this is a surjection, but maybe not a bijection. But still, this ends up being like a very useful notion of finiteness. Okay, are there any questions about that? So it's closed under Kuratowski finite unions. So we might say, what about Kuratowski finite joins? So suppose we have a join semilattice now, and we have a Kuratowski finite subset. I claim that the join of this exists. Now, it's not obvious that it exists, right? Because we know that you can take, say, joins of 2 elements or 3 elements or 4 elements. So that we would be sure of. But this is this arbitrary thing, which is some quotient of this numeral. So we need to check that we have joins of Kuratowski finite sets. And it's actually important that it's joins. If it were addition, it wouldn't be true. But it is true for joins. We need a stronger version of finiteness for addition. But in the case of joins, this join will exist, and we can explicitly compute it by taking the join over like whatever indexing set we have for the Kuratowski finite set. So how do we prove this? Well, we just show it's a join by showing it's the least upper bound. So suppose we have some element in S, our finite set. Then, okay, we have the surjection, right? Surjection from N. So there must be some index that maps to S. And then S is E of J, and then this is less than this join. And so this is an upper bound for everything in S. On the other hand, suppose we have another upper bound. Then for every J element of this set brackets N, we have that E of J is going to be less than or equal to U, because E of J is an element of S, right? And this is supposed to be an upper bound. But this then means that the join over all of these EJs is also going to be less than or equal to U. And And that's what we want our least upper bound to be. So it shows that this is actually the least upper bound. It's smaller than any other upper bound. So notice what we're using here is we're using the fact that we're kind of implicitly using idempotence in a sense. I did the order theoretic proof, but the point is that if it were, we're allowed to repeat things in our list, and it won't actually change what the answer is. If we were doing addition and we accidentally repeated things in our list, it'll completely mess up the answer, right? So the fact that we can use these Kuratowski finite things where you can sometimes repeat things in the list, it's important that we use doing an idempotent operation, but in this case, it does, everything works. Okay. So now we can see, we know that these sets are closed under Kuratowski finite joins and things. And we know that whenever you have a join semilattice, you're going to get the Kuratowski finite joins. So we now suspect that maybe the power set is given by the Kuratowski finite subsets of your particular set, and then just a union. And this is the case. So this is the free join semilattice. So it's certainly a semilattice, because you can take unions of Kuratowski finite things and they're still finite. So we're now going to take the unit of the adjunction to just be the thing that takes an element and puts it in a singleton set. That's Kuratowski finite. And now we need to show that the universal property is satisfied. So we take L to be any joint semilattice, and we consider a map from G into L. This is an arbitrary set function. And we want you to define a function that goes from this candidate free joint semilattice. So we kind of do the obvious thing, right? We say we will take the map applied to S to be the join of all things in S of f of S. And we need to check this thing exists, right? But this exists by the lemma, because this will be a Kuratowski finite join. So we showed that that will always exist, because L is a join semilattice. And this is what we're forced to do, because we're forced to send the singletons to themselves so that the diagram commutes. And then we also force that it preserves joins. So this completely determines what we need to do. And then you need to check that this definition actually does send 0 to 0, and it does preserve the finite or the binary join, but that's very easy to do. So, okay, so we can do that. Okay. Good. So I've been working with joins because it's more natural when you're talking about unions to make them joins, but actually we wanted the meet semilattice, so we need to reverse the order. So the meets are going to be given by unions, which is maybe a bit harder to think about, but that's how it is.
G is just a set.
Yeah, so G is just an arbitrary set. I'm calling it G for the set of generators. Yeah. Okay, so this is, we've now worked out how to take a set and give a meet semilattice. So now we should take a meet semilattice and give us a frame. And the idea is we use this idea of a down set. So you want to be able to take kind of arbitrary joins. If we maybe think about it like this. So the free meet semilattice was taking finite subsets, right? Now you might think if we take arbitrary subsets, that would be rather than taking finite meets that would take arbitrary meets or something. So we maybe want to take some of our arbitrary sets in some sense, but it needs to be compatible with the order we already had. So actually what we want to do is we want this notion of a down set. So a down set in a post set is just a set that whenever it contains an element, it contains any small element. And for every element, there's some kind of principal down set, the set of all things lying below it. And it's very easy to see that the down sets on a post set form a frame, essentially for the same reason that the power set forms a frame. So if you take intersections and unions of down sets, they're still down sets. So it'll form a frame. And we claim that the free frame on a meet semilattice M is just the frame of down sets. Okay. So I have a proof here, and I think there probably won't be a huge amount of time to go through all the details, So I think I'll omit the proof. You can look at it later if you want it. But it's exactly pretty much the same as what we did before, right? It's exactly like we did for this free meat semilattice. We just have to define things again in this obvious way by taking the joins, and everything works out. So I will leave the details maybe for you to check if you're interested. But it's pretty much the exact same story. We just check that this gives the free result. Okay, so now we can compute the free frame. And the way you think about it, so what is an element of the free frame? It's a downset of some kind of finite, like for the finite subsets of G, but now that these finite subsets are ordered in the reverse way. Okay, so maybe that's a bit of a confusing thing, but it's a set of finite sets. So what is the set of finite sets representing? Well, in the meat semilattice, this finite set is representing a formal meat. So we're going to have some kind of, in the finite set, you just think of taking the formal, like, finite meat of all the elements in the set. And this downset we think of as a formal join. So you think of this as describing some kind of formal join of finite meats. And it makes sense that an element of a frame should be of this form, because these are the operations used for a frame. So the kind of generic element you can write of a frame is of this form. And you might think, but what if I want to take then further meets and further joins and stuff? But it turns out because of distributivity, you can always get them into this canonical form where it's a join of meets. So this is kind of the content of this being the free frame, that this set of finite sets, you think of it as being this arbitrary join of finite meets. Okay. So any questions about what we've done so far?
This is down in the reverse order.
Yeah, so you could say it's an upset of the finite set. So yeah. But then it's kind of the whole order's reversed, because we really want these finite sets to be meets. But yeah, so it's just so this is just some set of finite sets, and what this big set you think of as being a join, and the smaller finite set you think of as being these formal meets. So that's really how you think about it. But the big point is the free frame exists, and it wasn't obvious that the free frame necessarily existed. Like, if rather than having just like if we didn't have the distributivity law, for example, and we I think that might not exist then, like the free structure. So I'm not completely certain about this, but certainly if we didn't have the distributive law and we had arbitrary meets and arbitrary joins, the free structure wouldn't exist. So it's kind of special that this exists, but it does. The free structure does exist.
So if I take a finite set and then I take its down set,
yeah,
what's that the join of?
So I mean, we've taken formal joins, right? So for the free structure, the elements are supposed to be these like formal, like freest possible join operations.
So the downsets are the elements.
Yeah, exactly. So maybe it's helpful to consider like an explicit example. So yeah, so if we take some kind of meat semilattice, like, I don't know, like this. Sorry, this isn't a meat semilattice, this is a joint semilattice. Let's oh, and it does need to have a largest element. Okay, in the finite case, of course, if you have finite meets, you have finite joins, so maybe that's not very interesting. But okay, so you take something like this, and you want to take the free frame on it. So it says that you can take, you take arbitrary downsets. Now, the reason you take downsets is if you want to take a join of a set, it's the same as taking the downset generated by that set, because adding additional elements to the join that are smaller than the elements that already exist in the join doesn't change anything. So in the frame, if we're going to take formal joins of this, we might say, okay, we could take a join of this and a join of this, so the join of these two elements, but that's the same as also including all these smaller elements in the join, right? Because they're smaller, they wouldn't change the answer. So our formal joins actually involve downsets, so all of these things would be included, because all of these different joins would actually be the same thing. So those kind of need to be identified. But now we can take the join of these formally. So it won't be this, it'll be something smaller. So that's kind of how things work. Okay. Yeah. So the elements of the frame are downsets on this semi-left.
Yeah. Things that were different in the set. Distinct elements in the set you started with are still distinct.
I guess that's a question. You can like ask that question, and it would be a theorem that you would show that this is actually this inclusion of the generators is injective, but it will be injective. Yeah. For example, if your algebraic structure was there are no operations and the only axiom is that x equals y for all x over y, then when you take the free structure, that won't actually be injective. Because if you take any two generators, they get mapped to the same thing for the free structure in this ridiculous degenerate algebra. But it turns out for frames like it. Okay, so now we have free frames. So now we can construct presentations, right? Because what we need to do, oh no, I assume I can just get rid of this. Okay, so what you need to do is you take the free frame on on G, sorry, and then we want to quotient so that these relations hold. So we quotient so that the relations hold, but that means we want to talk about quotients of frames. Okay, so we've spoken about the first part, taking the free frame on G, but now we want to quotient by these relations. So how do we do this? Okay, so in order to construct a quotient frame, well, again, as I keep on saying, frames are algebraic structures. So if you had a general algebraic structure and you wanted to compute a quotient, you would use a congruence, and that's what we do here. So a congruence, it's an equivalence relation, which is also a subframe of the product. So that's just because it needs to respect the frame operations. So usually we quotient in set, we quotient by equivalence relations, and frames we quotient by congruences. And whenever you construct the usual set quotient, it's quite easy to see that you can, that this will actually give a frame quotient with kind of an obvious notion of frame operation. So if you want to take the meet of A and B, then that's just going to be the meet of AB. You might notice for join, you might think you need to take choice. You might need to use choice here because they're an arbitrary number of things, and how do we pick what the generators are? But it turns out you don't need choice because frame maps have right adjoints, so you can actually always pick canonical representatives. So that's maybe a subtlety, which I'm not going to go too much into, but I guess the point is it does work. So when we look at the congruences, actually interesting things happen. So you can consider the lattice of congruences on a frame, and it's closed under intersections. So it forms a complete lattice, because if you have arbitrary intersections, you can also construct joins. And so we can consider the least congruence generated by a set. So we can take the intersection of all the congruences containing a relation, and we'll call this the congruence generated by R. And we'll write it with these kind of triangle brackets. So now, if we kind of write triangle brackets around G to mean the free frame generated by G, and we're writing triangle brackets for R to mean the congruence generated by R, then we can kind of do the strange, like, notational alchemy, where we say this presentation, you can just kind of add in the extra brackets and say that the frame presented by G generated G in relations R. What you do is you take the quotient of the free frame on G, quotiented by the congruence generated by the relations on R, because the relations R will be some, like the way the relations work is that these formal expressions, right? Some formal expression equals some other formal expression. So you can think of this as an element of the free frame on G, or as, well, that cross itself. So this makes sense. So now we actually know, in theory, if you knew how to compute with these congruences and things, we would be able to construct these presentations. So we now know that they exist. Any questions? Okay, but I think we'd like to understand these quotients a little bit better.
I have a question.
Oh, good, yes.
I didn't get how you actually calculate the quotient of a frame.
Yeah, so I didn't tell you in complete detail how it works, but the idea is we have some equivalence relation on the set. So because it's an equivalence relation, we can take the set quotient, right? So that gives us a quotient set. And then you need to work out how you put the operations on this quotient set. And I was saying, so you might have something that's the equivalence relation of A meet the equivalence relation of B. And the way to compute that operation is you can just say that's the equivalence relation of A meet B. So this puts a meet structure on the quotient, and then that gives an order structure for the quotient. And it turns out that this order structure actually gives it the structure of a frame. Does that make sense?
Yes, thank you.
Okay, great. Yes.
I mean, this quotient, I mean, it's not, I mean, R is not a subframe.
No. So that's why we generate. So that's why so R is not a subframe or anything. R is just a set. But you can take the intersection of all congruences that contain R.
But that would give you a subframe of G cross.
Of the free frame on G cross G. Yeah, cross.
So is it that product?
So that is a congruence. So that gives a congruence on the free frame on G. So you can take a quotient by it.
Oh, I see. This is a notation for congruence.
Yeah. Okay, great. Good. Yeah, sorry. So I'm going through this quite quickly because I'm assuming people have maybe seen how to take quotients of other algebraic structures, but hopefully it's somewhat clear. Okay. Okay, good. So we've spoken about these quotient frames, but we're doing point-free topology, right? So what kind of topological thing is the quotient frame going to correspond to? So there are a few things we can think about. So frames are supposed to be dual to spaces, right? There's this kind of contravariant adjunction between them. So we expect that if we have a quotient of a frame, that should somehow correspond to a subspace, right? Because quotients go to subobjects. Okay. Another way we could think about this is a quotient in kind of logical terms is adding axioms. So we're adding axioms, so we want to get fewer models that satisfy these axioms. So only certain ones of the models will satisfy them. So if we add additional axioms, this is again something like some kind of subobject. And we're keeping the propositions, of course, the basic propositions the same. We're just adding axioms. The next thing we could think about, suppose we have a topological space X, and then we have some subset of X. Then we can have a map that takes the intersection with the subset. So it just kind of restricts every open to be the one restricted to the subspace. And this is, in fact, this is a surjective frame homomorphism from the frame of opens of X to the frame of opens of the subspace. In fact, if you think of the subspace inclusion with its usual topology, this is precisely the frame map induced by that inclusion. But this is a surjective frame map. So we started with a subspace and we've got a surjective frame map. So again, this is giving us lots of evidence that frame quotients should somehow correspond to subspaces. So what we call them is we call them sublocales, right? Because we aren't working with topological spaces, we're working with locales. So a frame quotient we will call a sublocale when we're thinking in the opposite category, in the category of locales. Okay. So if we're thinking of these as sublocales, subspaces, there should be a notion of open subspaces, closed subspaces, things we're familiar with from topology. So we'd expect for every element of the frame, right? We call the elements of the frame opens. So we really expect it to correspond to some kind of open subspace, right? Some open sublocale. But an open sublocal would be given by a quotient. So some of the elements of the frame need to correspond to quotients. So how does this work? If you think about it, you'd really expect each open to kind of give you a frame corresponding to the downset of the open, all the things lower than that open. I mean, if you think in a topological space and you take an open set, the open sets in that subspace, in that open subspace, are going to be the open sets that are kind of contained in that open set. So this is very intuitive, but now we need to turn it into a quotient. So what we do is we take a meet with A. This is also quite intuitive if you think of this idea that I told you for a general subset of a topological space, you take meets. So again, you just take meets with A. So you start with an element in your big frame, and you take a meet with A, and that gives a surjective frame homomorphism onto this downset of A, which is also a frame. So, and this is actually a frame quotient. And it's maybe useful to think about the corresponding congruence. So we use this notation delta A to mean this congruence corresponding to this open quotient. And whenever you have a frame homomorphism, of course, you get the way congruences work is you get a congruence by saying when you identify, you kind of relate two elements when they get mapped to the same thing. So we'll say that U and V are related if they get sent to the same thing under this quotient map, and the quotient map says meet with A. So U and V are related when U meet A equals V meet A. And that gives us a particular congruence. And I claim that this congruence is also the same as the congruence generated by saying that A is related to 1, so 1 being the largest element of the frame. So in some sense, we say, I want A to be everything there is. So that corresponds to taking the subspace corresponding to A. So why is this true? So certainly note that A, 1 is an element of this congruence. You just need to check that A meet A equals 1 meet A. So now we need to check the other way around. So we need to check that if we have any elements of this congruence, that they are somewhat generated by setting A equal to 1. So we can suppose that we have U and V such that U meet A equals V meet A. And now we can consider the congruence generated by A and 1. Well, because it's a congruence, it satisfies reflexivity. So that means U is related to itself in this congruence. And we certainly know that A should be related to 1, because that's the thing we put in by hand. And now, because it's a congruence, it should be closed under finite meets. So we can take the meet of these, and we can get that U meet A should be related to U meet 1, which is just U. So U meet A is related to U. Okay. Now, in a very similar way, we get that V meet A is related to V. But now by transitivity, we're going to get that, so if U is related to U meet A, and U meet A equals V, and V meet A is related to V, we get that U is related to V. And that's what we wanted to prove. So this completes the proof, and it shows that the open congruence is just what you get by setting A equal to the top element. Okay, good. So yeah, I guess I will also say maybe what in logical terms this is saying. So A corresponds to some kind of proposition. And when we say A equals true, we're saying that A holds. So if A holds, it means we're in the subspace corresponding to A, right? So again, this makes sense from all the perspectives. Okay. Of course, you also want to talk about closed sublocales. So every element in your frame should also correspond to a closed sublocale. But this is like everything that wasn't in it. So what does that mean? Well, it turns out it's kind of dual. So rather than setting A equal to 1, we set A equal to 0, and we generate a congruence. So what's that like? That's like saying that A, the set, this kind of open set A, is nothing in our space. So in other words, we're outside of it. Or logically, it's saying that A doesn't hold. So in other words, we aren't in the set given by A. Okay, so we can prove, like the previous proof, but dually, we can prove that the congruence generated by this is actually the things where you say U join A equals V join A. So you just use joins instead of meets. And it turns out that this quotient ends up being isomorphic to the upset of A. So rather than the downset of A, it's the upset of A. And the quotient map takes a join with it. Now, this is all maybe a little bit less familiar because you don't generally think about things in these terms in point set topology. You don't usually think of the closed space of the opens being given by all the opens that contain the complement of the space, but you could think about them that way, because if you have some kind of closed subspace and it has some complement, for any open in the subspace, like it comes from some open in here, and then you can take the join of that with the complement, and then you get this entire thing. It's the entire space, and it goes in here. And this can be thought of as a good representative for the open corresponding to this. So there's kind of some way that you can think about it. But yeah, does that make some sense? Okay. So then there's a lemma we can prove, and that is that the open and closed sublocale given by an element A are complements in the lattice of sublocales. So here I'm talking about the lattice of sublocales. We know that the congruences form a lattice, right? In fact, I didn't mention this. It's very interesting that the congruences actually form a frame. So there's some weird thing going on that the congruences themselves form a frame, but we won't be using that. They form a lattice, and there's this relationship between the congruences and the quotients, right? But it's order reversing. So if you have a larger congruence, that means you identifying more things. So it becomes a smaller quotient. So the order on the quotients and the congruences are reversed. And so the lattice of sublocales has a dual order to the order of congruences. But if you have a complement in one, it's still a complement in the other. So I decided to write this as saying they're complements in the lattice of sublocales, because that's kind of what more corresponds to the subspaces. And you can prove this quite straightforwardly. I haven't included the proof, or well, rather, I didn't include the proof on the slides. However, if someone's very interested, I could do the proof on the board. The main thing it uses is this idea that if x join A equals y join A, and x meet A equals y meet A, then x equals y. So this is true in any distributive lattice. And I could give you a proof if you wanted, but this is really the core idea. And you can use this to show that, that the open congruence, so in other words, this is the closed congruence, and the open congruence are complements. So I could prove this, but I don't know whether it's necessary. Does anyone desperately want me to prove it? No. Okay, good. So you can believe me that this is true. Okay, so we've spoken about open sublocales, closed sublocales, and their complements. That's really exactly what we expect. Okay, so now we can maybe kind of test some of our understanding with an example, a very simple example. We take a discrete space. So if you have a set, we're very used to thinking of a set as a topological space with a discrete topology. And in fact, the space is sober, which you might recall means that it actually corresponds to a locale, like there's no information lost. So you can think of a set as a locale. And the opens, the frame of opens will just be all subsets, right? So it's going to be the locale given by the power set of X. So the power set of X is a locale because the subobject classifies a frame. Sorry, so the power set of X is a frame because the subobject classifies a frame. And this is the kind of, this frame is the frame of opens of the locale corresponding to the set X. And open sublocales of a discrete locale X should just be subsets. And that's, again, very believable, right? Because the elements of the frame are elements of the power set. So they are subsets. And so the opens are subsets. And then if you think of the downset, remember that's going to be the quotient frame, the downset on a particular subset S, that's going to be isomorphic to the power set of S. So again, this is quite easy to see just by thinking about how power sets work. So this is very intuitive. So the open sublocales are precisely the subsets. And that's what we wanted. That's what we were already hoping to be true. Now, since open sublocales and closed sublocales are complements, if you have a sublocale of a discrete space, which is both open and closed, that means it is open, so it's a subspace, but it's closed, so its complement's a subspace, which means it has a complement subset, which means these correspond to decidable subsets. So the Clopen subsets of a discrete space, the Clopen sublocales, are the decidable subsets. So again, this gives us a topological understanding of what these decidable subsets are. They're the clopens. Now, what you might notice is this means that closed sublocales of a discrete space are weird. They aren't necessarily discrete, or like they don't correspond to a set necessarily. They're kind of a bit strange, but you can understand them by their complements. So this gives you some kind of understanding that if it's both open and closed, it should be decidable. So again, this.
Yeah. So obviously opens correspond to verifiables and closed correspond to refutable.
Yeah. Yeah, good. So from that point of view, this is a proposition which is both verifiable and refutable. So we can say it's decidable. You can tell when it's true and you can tell when it's false. So you know everything about it essentially.
Yeah, so from first principles, you could have figured out that clopens were the decidable one.
Yeah, good point. First principles, if you buy, I guess, this verifiable interpretation, which you should. So yeah. But you could say this is showing that the theory actually works, I guess, Peter, that you're that the verifiable interpretation is sound in some sense. Or okay. Good. So what I just want to finish today with is that we can talk about preimages of sublocales. So if you have a subspace, you often want to take its preimage, for example, an open, and you can define this just categorically. So if you have a function f, and then you have a sublocale s going into y, you can take the pullback, and this will give you the preimage under f, just kind of usual categorical abstract nonsense stuff. One thing I should have mentioned is that categorically, you can understand these sublocales as being regular monomorphisms or extremal monomorphisms or things like that.
There's one thing on that issue is are surjective frame homomorphisms always quotients?
Yeah, so we define surjective homomorphisms to be quotients. They aren't the same as epimorphisms. They're the same as regular epimorphisms, but yeah, they.
Oh, okay.
Yeah.
Oh, I see. And so surjective. I mean.
Yeah, surjective is the right notion. It turns out. Yeah.
Okay.
Yeah. So it turns out in any algebraic theory, it's usually the surjective ones that are the well-behaved things that act like quotients.
I was just wondering what this with subspaces. I mean, they're not just.
Yeah, it's true. But we're talking about surjective on the opens as opposed to surjective on the points or anything. Yeah, good. Yeah. So it really is the surjective ones. So by taking pullbacks in this way, this actually gives us a functor. So we can take the sublattice of any the kind of lattice of sublocales, and then on morphisms, we get a contravariant functor by taking pullback. So and this gives us an order preserving map. So actually, we get a functor, a sublocale functor. So on objects, it gives us the sublocale lattice, and on morphisms, it takes this preimage operation. And actually, I say by standard algebraic arguments, essentially take the opposite category. It's in frames. There's a certain push out, and you can work out kind of, if you think through the details, what the congruence is associated to this pullback operation. And it turns out the congruence that you get is you just take the congruence you had before, and then you take its image under the frame map graph itself, and then you generate a congruence. So again, that's maybe somewhat intuitive. For example, if this was the entire space, that would be the congruence, which is just a quality. And then this says that when you take this preimage, you're going to get the congruence associated with f, which is like if f is a subspace, it'll be the congruence, it'll be the kernel of the frame map f. And yeah, so that's maybe kind of what you expect to happen. It will restrict it in the kind of the obvious way. But yeah, so I have one more slide, but I think this is time, so I will do that next time. But yeah, so any questions or anything like that? Yeah, good. So, I guess I want to also mention that preimages of open/closed sublocales are open/closed, because again, you think an open thing is just generated by a comma 1, like a is identified to 1, and then you take the image and it'll still be something identified to 1. So you can see that if you take the pre-image of an open sublocale, it's open, a closed sublocale is closed, everything as expected. And then next week we will do images as opposed to pre-images. But okay, that's all I had to say. Right. So are there any particular questions online or anything? Or general questions? I don't. No, okay, good. So what we'll do next week is we will talk a little bit about compactness and overtness and things. So Peter spoke about compactness earlier, well, last week, I guess. Not online, but in a different seminar. But I'm going to be talking a lot more about compactness and overtness thing in point-free topology. So compactness you all have heard of, overtness you won't have heard of. So if you're interested in it, stay tuned, I guess. But yeah. Okay, great.
Thank you so much.
Okay, sure.